All right. Um, Good afternoon, IB Physics SL. Mr. Pettibone here. Today we are going to be doing the, looks like we're going to be doing the odd questions from this lovely paper one, which is the multiple choice part of the IB exam. And for today I've chosen May 2018. You can see M18, time zone 1. Okay? May 2018, time zone 1. Hey, Spicy Pepper. A couple of updates. Update number 1, I got my Crocs. They're lovely. They're extremely comfortable. I don't think I'll need to wear socks for the next couple months because I have my Crocs now. And I also I had told you guys about how I was interested in axe throwing, and so I got a throwing axe from Amazon. So it's not very sharp. I think it needs to be sharpened. I can't I can't do one of those like cutting paper where you go. Have you ever seen those commercials where they are selling you knives and then they have like pieces of paper or tomatoes and they're just going like that. So it's not that level of sharpness, but yeah. All right. Sofa, you should totally get yourself a throwing axe. The only thing about this throwing axe is that when you buy them, you have to cut the handle to length. So I haven't decided how long I want. Probably I want the throwing axe to be maybe like the handle to be right here. So I'm going to have to cut this part off with a hacksaw or something. You can find throwing axes for like $15 on Amazon, 15 to 20 bucks. So that one was 20 bucks. Just be safe out there. Have fun, be safe. All right. So I'm doing the odd questions. Student measures the radius of a sphere with an absolute uncertainty of delta R. What is the fractional uncertainty in the volume of the sphere? Okay. So what we want to do is we want to notice that the volume of a sphere is 4/3 pi r cubed. Okay? So what that means, remember when things are multiplied together or divided, their percent uncertainties add together. So that means that the percent uncertainty in volume is going to be equal to the percent uncertainty in volume is going to be equal to the percent uncertainty in 4/3 pi plus 3 times the percent uncertainty in R. Now, why is that? It's because you have 3 factors of R, so you have percent uncertainty in R plus percent uncertainty in R plus percent uncertainty in R. Okay? Now, 4/3 pi is just a constant, so it has no percent uncertainty. So we just have that. The percent uncertainty in R is going to be delta R, Alt J, R over R times 100%. Okay? So what does it mean by the fractional uncertainty? That just means you don't multiply by 100%. So the fractional uncertainty in volume is 3 delta R over R, which is option B. Okay? Question 3, an object is projected upwards vertically at time 0. Air resistance is negligible. The object passes the same point above its starting position at times 2 seconds and 8 seconds. What was the initial speed of the object? So I'm going to be using the kinematics equation. Delta x equals v naught t minus 5t squared. Now, why did I say that? I said it because 1/2 g is 5, okay? So we know that the elevation at 2 seconds and 8 seconds are the same. So what I'm going to do is I'm going to put an equal sign, and on the left-hand side, I'm going to use that equation evaluated at time 2, and on the right-hand side, I'm going to evaluate it at time 8. So I have v naught times 2 minus 5 times 4, because 4 is 2 squared, equals v naught times 8 minus 5 times 64, because 8 squared is 64. So I want to rearrange this equation. It looks like 5 times 64 would be 320. So I have 300 equals 6 v naught, which says that v naught equals 50. So I think the answer would be A. All right. Question 5. An object falls from rest from a height h close to the surface of the moon. The moon has no atmosphere. When the object is fallen to a height h over 4 above the surface, what is the kinetic energy of the object divided by the potential energy of the object? The kinetic energy at h over 4 plus, or divided by the gravitational potential energy at h. So, if you are at height h over 4, according to MGY, you've only got 25% of your initial gravitational potential energy, which means that the rest of that energy is kinetic energy. So if you're at height h over 4, your kinetic energy is going to be the remainder of the gravitational potential energy you had at the start. So you actually have 3h over 4 of kinetic energy. Okay? And then we got to divide that by the initial gravitational potential energy, which was just mgh. So dividing those, we get that the ratio is just 3/4. So I would say the answer is A. All right. Number 7. An increasing force acts on a metal wire, and the wire extends from an initial length L0 to a new length L. The graph shows the variation of force with the length of the wire. Wow, that's a really stretchy wire. The energy required to extend the wire from L0 to L is E. Then the wire contracts to half its original extension. What is the work done by the wire as it contracts? Okay, so initially the wire has an elastic potential of 1/2 K L squared. Okay, afterwards it has because it contracts to half its original length, it has a potential energy of 1/2 k times L/2 squared. So if we subtract those two, what we get is 1/2 k L squared. So subtracting those two, we get this times 3/4. Right? Because you have 1 minus 1/4. Because 1/2 squared is 1/4. So this is very similar to the last problem we did, actually. Now the change in potential energy of the wire is going to be equal to the work that it did. Okay, so it's going to be 0.75, which would be C. All right. Let me see if I have any questions. Hey, Christian. All right, going to number 9. An object is moving in a straight line. A force F and a resistive force F, little f, act on the object along a straight line. Both forces act for a time t. What is the rate of change of momentum with time of the object during time t? This is requiring you to know the sneaky form of Newton's second law, which says that that net force equals change in momentum over change in time. So rate of change of momentum means change in momentum over change in time, which is just equal to the net force. The net force is big F minus little f, because they're going in opposite directions. So that's the answer. The answer would be B. Number 11. What are the units of specific heat capacity of copper divided by specific latent heat of vaporization of copper? Okay, that's pretty straightforward. So we know that if something is in a certain phase, the heat required to change its temperature is mc delta T. Okay? If something is changing the phase, then the heat required to change the phase is mL. So if we do a units of each of these equations, we get that the units of specific heat capacity is joules per kilogram per Kelvin. And we get that if we take the units of specific latent heat, we get joules per kilogram. Okay, just from taking the units of those equations, which says if we do the ratio of those units, we can see that the joules per kilogram gets canceled out, and we just get 1 over Kelvin, which would be the answer C. All right. 13. A first harmonic standing wave is formed on a vertical string of length 3 meters using a vibration generator. The boundary conditions are that it is fixed at one boundary and free at the other. Okay. The generator vibrates at a frequency of blah. What is the speed of wave on a string? All right, so there's a couple of ways we could do this. So let me draw what the first, so this is a closed, open instrument. So let me draw what the first harmonic looks like, just to remind you. So if you have a closed open instrument, it kind of looks like this. Okay. And then the first harmonic is the one that kind of goes like that for one half of the cycle, and then like this for the other half of the cycle. So it has a node at the top, and it has an antinode at the bottom. Okay? So, what that means, we can see that this is, the first harmonic is actually a quarter of a wave because it has half of a crest. So that means that lambda is actually 4 times the length of the string. So it would be 12 meters. So then we have V equals lambda F, which would be 12 times 300. And we get, so that would be, what, 3,600? 3,600 meters per second, which could also be written as 3.6 kilometers per second. So I can see that the answer D is 3.6 kilometers per second. Number 15. Whoa! Someone put a lot of work in that. I wonder, it's like 3D graphics. Holy cow, that's exciting. I'm like getting dizzy looking at this. The diagram shows an interference pattern produced by 2 sources that oscillate on the surface of a liquid. Which of the distance shown corresponds to 1 fringe width of the interference pattern? So one of the things that we were talking about is this whole idea of, I'm going to have to draw this. If we wanted to think about intensity, if you were to graph intensity, it would kind of look like this. Okay? And because you can see that there are these spots right here where the wave is 0. That's a spot of destructive interference. And then there are spots where we can see the wave, like in between the 2 spots of destructive interference, like right along there, where it's constructive interference, okay? So a fringe corresponds to one of these bumps. So like this width right here, okay? That's called a fringe. It's a bump of constructive interference. And we can see that that would be option C, this width right there. Has the correct, see how it goes from destructive interference to destructive interference. All right. Number 17. A particle is displaced from rest and released at time 0. If you start from rest, that means you start out with no kinetic energy. So this answer is out because it has non-zero kinetic energy. See, non-zero kinetic energy. This one is out because it says kinetic energy at the start. These 2 are possibilities. But this one is out because it says the kinetic energy can be negative. The kinetic energy can't be negative. It's a square of something. It's a positive function. So the correct answer is D. Okay. Number 19. Ooh, okay. It's kind of cool. A liquid that contains negative charge carriers is flowing through a square pipe with sides A, B, C, D. A magnetic field acts in the direction shown across the pipe. On which side of the pipe does negative charge accumulate? Well, we've got to use the left-hand rule, okay, because it's a negative charge. And the velocity is along this way, all right? So I'm going to put my pointer finger in that direction. And then I'm going to put my middle finger with the magnetic field, which is to the left. And we can see that my thumb is going upwards. So that means that the negative charge is going to get pushed to the top of the pipe, which is side A. All right. Let me see if I have some questions. No questions. 21. Two resistors, X and Y, are made of uniform cylinders of the same material. X and Y are connected in series. X and Y are made of equal length, and the diameter of Y is twice the diameter of X. What is the resistance of Y is R. What is the resistance of this series combination? Okay. So what we have here, R sub S is going to be the resistance of X plus the resistance of Y. The resistance of Y is rho L over A. That's according to the resistance formula we learned. X has half the diameter of Y. Okay? Half the diameter. So if you half the diameter of a circle, then that means that the area is now 1/4. Why is that? Well, because it depends on R squared. So we have to square that 1/2. So resistor X has half the area, or sorry, a quarter of the area, which means it's going to have 4 times the resistance. So 4 rho L over A. So if we add 4 plus 1, we get 5. So R sub S equals 5R. So the answer would be D. All right? And they both had equal lengths, so I didn't have to worry about the length changing between them. Question 3. Newton's law of gravitation is equivalent to Newton's second law of motion? Nope. Because Newton's second law of motion is F equals ma. Option B says explains the origin of gravitation. No, it doesn't really explain why gravity is. It just explains how gravity is. So I would say that B is not the correct answer. Newton's law of gravitation is used to make predictions. Yeah, I mean, we predict where the planets are going to be. We predict where satellites are going to go, all using Newton's law of gravitation. So I would say it's definitely used to make predictions. And D, Newton's law of gravitation is not valid in a vacuum. Space is a vacuum, and planets are moving through space, so it's valid in a vacuum. So the answer's got to be C. Isn't that a weird little question to put in there? That's a bizarre question. 25. The average binding energy per nucleon of oxygen 15 is 7.5 MeVs. What is the total energy required to separate the nucleons of one nucleus of that? So that's the binding energy per nucleon. If we take binding energy per nucleon and we multiply it by the number of nucleons, that's going to equal the binding energy. So the binding energy is going to be 7.5 times 15, because there's 15 nucleons in there. So that's going to be what is that? A little less than 150, right? So that's got to be 113 MeVs. Now the binding energy is, by definition, the energy required to blast the nucleus apart. So that would be the answer. So that would be 113C. 27. The energy level diagram for an atom has 4 states, as shown. What is the number of different wavelengths in the emission spectrum? Okay. That's kind of cool. So the electron can jump, or the atom can jump between any of the states. And when it jumps between the states, it emits a photon of a certain wavelength. So this question is asking, how many different possible jumps are there in this system? So I could see there's a jump from the top level to the bottom level, from the top level to the next one, from the top level to the next one, like that. So that's 3. Or we could start at the next highest level. We could jump all the way to the bottom. Or we could jump to the one above that. Or what if we started at the very bottom and made, or almost to the very bottom and made that jump? So those are all the possible jumps. You can try and make other jumps, but you won't find them. So if I count up the number of lines, I see there are 6 lines. So that means that there must be 6 different wavelengths that we could get. That's assuming that each of these jumps has a different size, which I'm assuming that they are. Because if, for example, 2 jumps by coincidence had the same size, you would get the same wavelength for each one. Okay, 29. 3 energy sources for power stations are blah, blah, blah. Which sources are primary sources? Okay, I'm pretty stumped by that. I don't even know what a primary source is. I'm going to Google it. So I have another window that you guys can't see. I'm typing it into Google. What is a primary source of energy? Primary sources can be used directly as they appear in the natural environment. Coal, oil, natural gas, and wood so fossil fuel, I don't think that that's a primary source, because you can't just like put oil directly into an engine. You have to process it, so it's not a primary source. Pumped water storage, I would say, probably is a primary source, because you're not using you're not processing the water. And then nuclear fuel, I also think would be a primary source because you're just taking uranium from the environment. So I would say the answer is 2 and 3, but I'm not sure about that. You guys can check. All right. So that is the end of our journey for today. If you made it all the way through, I appreciate it. And I hope you guys have a wonderful afternoon. And I would love to hear from you guys in the Discord. I'm on Discord for an hour every day. No one ever talks to me. So make me less lonely. And I will definitely talk to you tomorrow, though. Bye.